My today's session is based upon three important topics. One is called discrete random variable, another is expectation, another is variance. So I shall go slowly and I will cover each topic one after another sequentially because each is dependent on the other. So let's begin with random variable. Now, I'm pretty sure, I am 90% sure if I ask what random variable is, before I could show you the definition which is in front of you, you could have replied it in this way. Random variable is a variable which occurs randomly. Vaguely you are all right, but that is not the actual case. Random variable is, as you can see, it is a function. It's a function defined from a set A to a set B. Random variable is a function. Amazing thing. Everybody knew so far that random variable is a variable. How can this be a function? Yes, but it is true. Random variable is definitely a function, and it is defined from a particular set which is called domain, another set which is called range. Okay. Now, what is the domain set? The set of domain, when we define random variable, is the set of all possible outcomes. And the range set is the subset of set of real numbers. Okay, so random variable is defined as a function from the set of all possible outcomes, means sample space, to a subset of set of real numbers. Let me clarify this by citing one example, which I have written below. Okay, when I prepared this particular note, please mute yourself. Please mute yourself. Please mute yourself. Now, those who are, when I took the class in the morning, this example was not there. I just discussed. Later, I thought it would be much better if I write this expression in detail so that you can all see. It will be much clearer to you. Okay, so I have, after this morning session with ECB, I have introduced this particular part. This particular table, in this particular chart in my note of discrete random variable. What happens is that if we toss two coins, okay, simultaneously, then you all know that the four possible outcomes are H, T, TH, and TT, right? Now we have made a chart over here where outcomes have been tabulated in this manner. Now suppose I am interested in counting the number of heads in each of these outcomes. What will happen then? Suppose I am denoting this number of heads by capital X. Now you see, if I apply X on HH, the count will be 2. If I apply X on HT, the count will be 1. If I apply X on TH, the count will be 1. X on TT, count will be 0. So you are getting some numbers, isn't it? 0, 1, 2. Suppose one of your friends is interested in counting the number of tails in this particular experiment. So he is getting another he is actually taking another notation, say capital Y, and when he is applying Y individually on each of these outcomes, he is getting YHH to be 0, YHT to be 1, YTH to be 1, YTT equal to 0, 2. Both of us are counting. I'm counting heads and he is counting tail. And suppose there is another person who is interested in counting the heads of the first coin. So you see, for HH, the outcome HH, the count will be 1. This will be HT. The count for HT, the count will be 1 because first coin is showing 1. And for TH, the count will be 0 because the first coin is showing no head. For last, the count will be 0 because none of the coin is showing head. So all these variables, all these notations which I'm using over here, all these counts are actually random variables. So what is happening is that for random variables, I'm starting from a set of all possible outcomes, and I'm getting some set of numbers. And you see these numbers 0, 1, 2, these are obviously real numbers, but I'm not considering all the real numbers together. I'm considering a subset of set of real numbers. Therefore, I mentioned here that a random variable is a function whose domain is the sample space and whose range is the subset of set of real numbers. Okay, and you can cite so many examples. These are not the only examples. Various other examples are there, and in various other way, you can define your counts, define your random variable for this experiment also. Now, let us move on to a simple problem, because I always believe in solving problems. Okay, there is not much to discuss. If we don't solve problems. You'll not be able to understand. So I have selected a very simple problem here. You see, the problem is, suppose that capital X is a random variable that takes on the values 1, 2, or 3. Now, probability of that X takes the value 1 is given to be 0.4. Probability that X takes the value 2 is given to be 0.1. We are supposed to find probability that X takes the value 3. Now, we know that sum total of all the probabilities must be equal to 1. So, probability that X takes the value 1 plus probability that X takes the value 2 plus probability that X takes the value 3 must be equal to 1. And from there, I can find out the probability that random variable takes the value 3, which is 1 minus P of X equal to 1 minus P of X equal to 2. And I'm putting the values over here, 0.4 and 0.1. And probability of X equal to 3 is 0.5. After that, what am I doing? I am plotting these values. Okay, so I've considered two axes. One is called the x-axis, in which I am putting the points 1, 2, and 3. And on the y-axis, I'm putting the probabilities, their respective probabilities. And what am I doing? Since one has got the probability 0.4, I'm putting a dot over here and dropping a line from that dot, and which touches the x-axis at 1. I am putting a dot corresponding to 0.1 and dropping a line from there to 2. And I'm putting a dot corresponding to 0.5 and dropping a line from there perpendicularly, which touches x-axis at 3. So actually, I'm getting a line diagram. This is called the probability plot, probability distribution plot. And you see this 1, 2, 3, all these values are discrete values of capital X. So therefore, this random variable capital X in this example is a discrete random variable. Not only this, the example which I cited above, this example, the random variables was discrete because it considered 4 discrete items, HH, HT, TH, and TT. Now, our next job, one more thing, I have tabulated, I have made a chart, I have prepared a chart over here. You see, I have put all the values given in the question for X, and I have denoted their respective probabilities by Px. Okay, so one has got the probability 0.4, 2 has got the probability 0.1, 3 has got the probability 0.5, and these probabilities are known as probability mass function, or probability, or in short, it is written as PMF, probability mass function, or PMF. And you see, sum total of all these probabilities is equal to 1. Now, probability mass function has two properties. One property that each probability must be non-negative. That means it should be greater than or equal to 0. And sum total of all these probability mass functions should be equal to 1. So if I give you a chart where you find that the sum total of this probability mass function is not 1, that indicates that you are not dealing with a complete chart, or some probabilities may be missing. Okay, so this is a kind of indicator which tells you that you are dealing with an exhaustive number of cases, exhaustive number of probabilities. Okay, so, and one more thing, why do we call them probability mass function? Why not simple probabilities? It's just because it is just a naming. Okay, I'm just naming it as, just like my name is Shovik, these probabilities are named as probability mass function. One vital reason for which we do this is to distinguish these probabilities which corresponds to discrete random variable from the probabilities which corresponds to continuous random variable. So when we shall study continuous random variable, we shall be dealing with probabilities once again, but their names will be something different. Okay, I shall tell those names when we shall discuss the probability, continuous probability distribution. One of you is has unmuted himself, so please mute a noise is actually appearing. Okay, please mute yourself, those who are present in the class. After we prepare the chart, after we prepare the probability distribution chart, our job is to calculate the expectation of the random variable capital X and variance of the random variable capital X. Okay, so how do we calculate expectation and variance? First of all, I shall tell you the technicalities by which we calculate these terms, expectation and variance for the random variable. And after that, I shall tell you what do they mean actually. Let me save the chat because people are actually writing their roll numbers. Yeah, that is done. Okay, so let us now move on to the part of expectation. What do we mean by expectation? If capital X is a random variable, the expectation of the random variable is denoted by EX and is defined as EX equal to summation over small x into probability of capital X equal to small x. Capital X is the mother variable, small x is the values which capital X are, small x are the values which capital X is taking at different points of time. So I'm calculating each probability, each value by their respective probabilities, and I'm repeating this process for each and every value, and I'm summing it over together. So if I apply this formula to our given chart, what we get for our given chart, the expectation of random variable is calculated as 1 multiplied by its probability 0.4, 2 multiplied by its probability 0.1, 3 multiplied by its probability 0.5, and we are adding them together, and the value is coming to be 2.1. Okay, what is expectation? I will tell you later on. Okay, let us now calculate the variance. So if capital X is the random variable, variance is denoted by Vx. Now Vx has got this formula: expectation of x squared minus expectation of x whole squared. Okay, expectation of x has already been calculated for the given problem, which is 2.1. Our only job is to find expectation of x squared, and here is the formula marked yellow. This is the formula is given as summation over x, all possible values of capital X, x squared multiplied their corresponding probabilities. So Ex squared for our problem is calculated as 1 squared multiplied by 0.4, means its probability, plus 2 squared multiplied by its probability 0.1, plus 3 squared multiplied by its probability 0.5 is equal to 5.3. And Vx is therefore calculated as, in place of Vx squared, I'm putting 5.3, and in place of Ex, I'm putting 2.1. So this 2.1 gets squared. So the result is, the outcome is 0.89. Now you see, I have calculated two items here: expectation of capital X and variance of capital X. What do we mean by expectation? Some people are very much confused about expectation. They think that expectations are nothing but as synonymous to probabilities. Okay, and expectations maybe expectations are having values lying between 0 and 1. But when they calculate expectation and they get values more than 1, they become confused. They can calculate expectation, but they don't understand what actually it represents. So let me tell you what expectation is. Probably in school, you have heard about frequency chart. For the frequency chart, for the frequency distribution like x/fx, the arithmetic mean is given by x bar, summation x fx by summation fx. We all know that arithmetic mean for the frequency distribution is calculated in this manner. Okay, if I replace the frequency, these frequencies by probabilities. Probabilities are also a kind of frequencies. The only difference is a special type of frequencies. What is the specialty of probabilities? Because if you take the summation, that becomes 1. In frequencies, that do not happen. So if I replace all fx's by px's, what we get? We get x bar equal to summation x px by summation px. Okay. Now, since px's are probability mass function, summation px is equal to what? Summation px is 1. So in the denominator, I am getting 1. So it is summation x px Okay, x bar becomes summation xpx. Let me scroll up. I wrote xpx to be expectation of capital X, and here also, after replacing all fx's by px, you are getting the summation as you are getting this as xpx, summation xpx, which is similar to expectation of the random variable. So from this simple calculation, what do we find? We have found that expectation of capital X is equal to x bar. Okay, but so therefore, when a random variable is given to you, when we calculate expectation, that means we are calculating the average of that random variable. So expectations are nothing but averages. So it can be greater than 1. Okay, and variance is nothing but the measurement of dispersion, how the individual points of the distributions are scattered around the average, how the values of the random variables are scattered around the average of the random variable. That has been calculated in the problem. So our expectation has come out to be 5.3, 2.1. This is the average of the random variable, and our variance, the measure of the variance, that means the data set is scattered around this 2.1 by the measure of 0.89. Okay, in the module 4, we have basic statistics. Okay, so when we'll study basic statistics, I shall be discussing these measures of central tendency and measures of dispersion in more details. Okay, let us now proceed with some more problems. So our next problem is this one, a practical problem. It's given in question number 2. We read the question along with me. The question says, a saleswoman has scheduled 2 appointments to sell encyclopedias. She feels that her first appointment will lead to a sale with probability 0.3. She also feels that the second will lead to a sale with probability 0.6, and that the results from the 2 appointments are independent. What is the probability distribution of capital X? The number of sales made. Okay. Read the question, keep on reading the question. Meanwhile, I'm explaining the solution to you. How do I solve this problem? Now you see the random variable denotes here the number of sales. Okay. Now, since it denotes sales, so there are 3 possibilities. First possibility, that there are no sales. The saleswoman couldn't sell anything. Second possibility, that she could sell only 1 item. Third possibility is that capital X equals to 2. That means she could sell 2 items. So I have got, if you think about the probability chart, I have got the values of X as 0, 1, 2. And to make the chart complete, I need to find the probabilities of these values of capital X. So let us together find out the probabilities. Probability of X equal to 0 means probability of no sale. And that means she couldn't sell any item in her first appointment, and she couldn't sell any item in her second appointment. Okay, so but you see the 2 appointments are independent of one another. Why they are independent? Because suppose she's selling items online and she's at the same time simultaneously dealing with 2 customers. One, she can sell, she may convince me, but she may not be able to convince you. So I'm buying from her, you are not buying from her. So whether I'm buying or not, that doesn't depend upon whether you buy or not, because we 2, the customers, are not communicating with each other. So she is dealing with us independently. Since this is the case, so these probabilities can be broken into 2 halves by a theorem of independent probabilities, and we get this multiplication sign in between. So we get probability of no sale on first appointment, probability of no sale on second appointment. And since the probability of a sale in the first appointment is 0.3, so no sale will be 1 minus 0.3. And for the second case, it will be 1 minus 0.6. So these 2 probabilities are getting multiplied, and the outcome is 0.28. So we have got the probability of X equal to 0 to be 0.28. Let us now calculate the probability of X equal to 1. That means only 1 sale. How many cases are there? 2 cases. no sale on the first item, on the first appointment, and one sale on the second appointment. This may happen, or one sale in the first appointment, no sale on the second appointment. These are the two mutually exclusive cases. So I am breaking them into two halves because you already know that probability of A union B equals to PA plus PB when A and B are mutually exclusive. So we are getting a plus sign over here. Now, probability of no sale on the first means 1 minus 0.3. Probability of one sale on the second means 0.6 plus probability of one sale on the first, that is 1 minus 0.6. Probability of no sale on the second, that is 0. So you calculate, you are getting the probability of 0.5. Second part has already been calculated. To calculate the first part, the third part, you can do it in two ways. What are the ways? Since we are dealing with probability mass functions, I can subtract the sum total of 0.28 and 0.54 from 1. But this would be much better if we can find out this probability directly from the case study. So probability of x equal to 2, let us find it out directly from the case given. So probability of x equal to 2 means probability of 2 sales. Only one case will be there. Remember, that is the most important point. Probability of one sale on the first and probability of one sale on the second. Because if you read the question carefully, you will find that the salesman is allowed to sell the item, one item per appointment and not two items. So other cases will not be there. Okay, it is mentioned in the problem. So only one case. And since the appointments are independent of one another, so probability of this will be multiplied by probability of that. And we'll get 0.3 into 0.6, which is 0.18. And this tallies with the given result, which I obtained by applying the property of probability mass function. So that's how we can calculate all the probabilities of the sales of the saleswoman. Okay. And after that, which I have not shown here, you can calculate, you make a probability chart. Okay, you put the values of x equal to 0, 1, 2, and all these probabilities 0.28, 0.54, and 0.18. And you can calculate again, once again, the mean means expectation of sales and variance of sales. Okay, so you do it by yourself. Let me proceed to the third problem of today's class. It's an important problem. A shipment of parts contains 120 items, of which 10 are defective. Okay, 2 of these items are randomly selected and inspected. Let capital X denote the number that are defective. Find the probability distribution of capital X. Here, in the previous problem, the concerned random variable was the sales by the saleswoman. But here you see the concerned random variable indicates the defective items. Since we are choosing two items from the shipment, so there are 3 possibilities. None of these items is defective, so capital X may take the value 0. One item may be defective, capital X is taking 1. 2 items may be defective. Both the items you have selected are defectives. So capital X may be 2. So there again, if you consider the probability chart, okay, if you think of the probability chart, you can say that there are 3 values for the random variables, x equal to 0, 1, and 2. Our job is to find the probabilities of these values one by one, just like we did in the previous case. So let us do it. Okay, hope you are understanding. If you do not understand at any point, you can unmute yourself and you can ask me. I shall be happy to help you. Okay, now to calculate the probabilities, we need to take the help of one information which is given in the problem. What is that information? The information is, you see, out of 120 items, 10 items are defective. Okay, so if we apply the classical definition of probability, the probability of defective item is 10 by 120, that is 1 by 12. So this probability is very important. So here I have written this below, that given the probability that the item is defective is 1 by 12. How did I get it? I divided 10 by 120. Now one by one, let us calculate the probability of 0 defective, 1 defective, and 2 defectives. Probability of x equal to 0. Probability of x equal to 0 means probability of no defectives. That means this can happen in this way, that probability that the first item is not defective and the second item is also not defective. Together they are both of them are not defective. Now you are choosing the items independently, although it is not mentioned explicitly in the question, but you are drawing the items independently. Okay, it is not like that you are drawing the item, you are selecting an item and you are seeing that, oh, it is defective, okay, and put it over there and you are selecting the next. That selection is not independent selection. That selection is dependent selection. We often go to the go to the market and to buy vegetables and fruits, and we do this kind of selection. Oh yes, apple to अच्छा नहीं है, चलो इसको रख देते, दूसरा apple को collect कर लेते. Now that is not independent selection, that is dependent selection. बाजार में जाओ, ऐसा हाथ घुसा के जो हाथ में आए उसको उठा के लेके आओ. Okay, so all these items have been selected independently. So I can apply the theorem of independent probabilities. Probability that first item is not defective multiplied by probability that second item is not defective. And since the probability of defective item is 1 by 12, so this will be 1 minus 1 by 12 multiplied by itself. And the probability is 0.84027. I forgot to mention one important thing in previous classes, that please students, whenever you will be calculating probabilities, it's my request to all of you, always write 4 to 5 digits after decimal point. It is a good practice and you will gradually understand what I said this. Right now, I'm not going to declare. Let us keep it secret. Okay, try to find out by yourself. Why did I say this? Okay, always, it is a good practice. Try to write 4 to 5 digits after decimal point. So that's why I have not written 0.84. I have written 0.84027. Probability of x equal to 1. Probability of x equal to 1 means 1 defective. It can happen in this way. First item is defective, but the second item is not defective. Or first item is not defective, the second item is defective. Now they are mutually exclusive cases. Okay, so I have got a plus sign in between. Probability of and the choices are independent. So multiplication theorem of probability has been applied. So probability of first item is defective is multiplied by probability of second item is not defective, plus probability of first item is not defective multiplied by probability of that second item is defective. So I have put the values over here. First item defective means 1 by 12 multiplied by second item not defective means 1 minus 1 by 12, plus first item not defective means 1 minus 1 by 12 multiplied by second item is defective means 1 by 12. And the calculated probability is 0.15277. Probability that 2 items are defective can happen only one way. First item is defective, second item is defective. Choices are independent, so I'm multiplying their probabilities, individual probabilities, and that is 1 by 12 squared, which is 0.006944. So I have got all the values for these choices of number of defective items. So when I have put these items over here, probability of x equal to small x gets the value 0, 1, 2, and the respective probabilities can be denoted by one of these notations, and these have been tabulated also. Plot the probabilities with respect to the values. You can do many things over here. Okay, if you want, so you can draw a line diagram of this probability chart, or you can calculate the average number of defective items and variance of defective items. Okay, so I am keeping this for you to do by yourself. This problem is important because I'm going to show you an alternative approach, and when I finish this, you will be amazed to see that something will pop up which you already probably know and probably have heard of. Now this problem can also be dealt in a different way. What is that? Suppose we term the finding of a defective item from a shipment as our success. Then that success has the probability 1 by 12, okay? And consequently, the probability of failure will be 11 by 12. Two items have been selected randomly from the lot size 120. Okay, now the lot size containing 120 item is my population. And the items which I have selected is my sample. You are going to get irritated from gradually when I'll be taking these names again and again, population and sample in BSM 301 class, because in statistics, we are always going to deal with samples to judge the population. Okay, so our actual job is to study the population. So our population size is 120, our sample size is 2. Now you see, we are supposed to find the probability of a number of defective items from these two selected items. If we suppose that there are small x number of defective items with probability of success 1 by 12 and lot size 2, this probability can be calculated as this. Probably you know this formula. Probability of x equal to small x is given as 2cx 1 by 12 to the power x 11 by 12 whole thing to the power 2 minus x, where x runs from 0, 1 up and 2. So we are calculating all of these probabilities individually by putting first x equal to 0 in the formula, then putting x equal to 1 in the formula, and then putting x equal to 2 in the formula. And after putting these values here, I'm getting the probabilities as 0.84027. For probability of x equal to 1 is 0.15277, and probability of x equal to 2 is 0.0069. You know the problem is of special, is a kind of special type of problem, and the formula which I have applied here is called the binomial probability law. Okay, in my today's class, I'm not going to discuss the binomial probability law. Binomial distribution will be discussed in tomorrow's class. Okay, and will be discussed in details. My objective here was to show you that a particular problem can be dealt in two different ways. And tomorrow I'm going to tell you why, when I could solve the problem of this finding out the probabilities of defective items from the lot by applying the theorem of independent probability, why do I need to apply some new formula or some other formula to calculate the probabilities? Why do we need to study these binomial probabilities and etc. and etc. In tomorrow's class, those things will be discussed in detail. Okay, so you see the values which I've got are same as the values which I previously got after solving the problem directly by applying the theorem of independent events. And since I have mentioned the binomial probability law, let me give you the definition. In today's class, the definition of binomial probability law is that a random variable capital X, which is said to have a probability distribution of the form probability of x equal to small x is equal to ncx p to the power x q to the power n minus x, where x takes the value 0, 1 to up to n, then x is said to follow binomial distribution, and the variable x is called binomial variable. Binomial variable is actually a kind of discrete random variable. Okay, and its probability mass function is given by this expression. So I hope you have understood what I have discussed in today's class. We started with probability distribution and probability mass function, and we discussed what discrete random variable is and what do we mean by expectation of the random variable and variance of the random variable. Okay. Tomorrow also, I'm going to discuss these things from a different perspective. Okay, and binomial distribution and some other distributions will be discussed in detail. Okay, once I finish this discrete random variable portion, we'll move on to the continuous random variable. Okay, so if you have any, my time is running out. Okay, the meeting will get cancelled automatically right now, and I'm almost done for today. So if you have any doubt, you can unmute yourself and you can ask me. questions. Okay, if you have doubts, then you can rejoin and ask me questions, and you are going to get this note by within 1 hour in Google Classroom, and I'm going to upload this video in the YouTube, so that everybody, those if you want to listen to what I discussed later on, you can revisit the video and listen to it. Okay, so do you have any question? If not, I'm going to cancel my today's meeting right now, and see you soon. See you tomorrow. Till then, bye bye, and stay healthy and stay safe. Okay.